Hey guys, welcome back. So we're going to get into lecture 12, which is about thermodynamics. We're going to talk about more of the laws of thermodynamics and how they relate to what we need to be discussing in terms of enthalpy, entropy, and free energy. Again, not all of those terms have been introduced yet, so don't freak out if you don't know what they are. So let's go ahead and get started, and as always, we will be doing a review from last time when we talked about enthalpy. At least I think we will. So, define an open system. So, an open system can transfer both matter and energy. Okay. Closed can only do heat, and isolated cannot do either. Exothermic. So, my exothermic sign is negative delta H, and that means heat given off. So, it's a product. Chemical energy is the energy that's stored in chemical bonds. The law of conservation of energy says energy can neither be created nor destroyed. Only change forms. So we can reorganize it, but we can't create it or destroy it. State function. A state function is independent of path. Name one. P, V, U, H are all. So one of those is fine. U, Q, and W. U is the internal energy. Q is heat. W is work. Is work a state function? No, most definitely not. And that's because it's dependent on the path that it takes to get there. So enthalpy is, so delta H equals delta U minus P delta V. That's a V, I swear. So enthalpy is the energy that is present in the thermal parts, so the thermal energy of our system. Really great definition. Is it a state function? Yes, it is. It is defined as a state function. Is enthalpy dependent on stoichiometry? Yes. Because if I make 2 moles of something, that requires twice as much energy as it does to make 1 mole of something. So that is important. What is the formula to calculate the enthalpy of a system? Okay, so it depends on what you're talking about here. So I can say that the enthalpy of my system is equal to the enthalpy of my products minus my reactants. I also know that the delta U of my system is equal to the negative delta U of the surroundings. So that's another way that I can look at that. I can calculate the heat evolved under the following conditions. I have 2 SO2 gas plus O2 gas going to 2 SO3. Delta H for that is given as negative 198.2. But out here, I have 44.624 grams of SO3. So 44.624 grams of SO3. Need a molecular weight for SO3. So I'm going to grab this. And this table we'll get to in a few minutes. But for right now, I'm going to go back to my molecular weight calculator. SO3 is 80.06 grams per mole. And I know that this is negative 198.2 kilojoules for 2 moles of SO3. So awesome. If I only want to make one, I'd have to divide that by 2, which is why the 2 goes on the bottom. Awesome. 44.624 divided by 80.06 times negative 198.2 divided by 2. And that gives me negative, and it's not going to fit there for crying out loud, negative 55.2 kilojoules. We can also calculate this. Oh, for the love of God, I'm so sorry. So 44.264 divided by the 80.06 times negative 198.2 divided by 2 moles, because there are 2 moles in this equation. So that gives me the energy that I need there. 67.93 grams of oxygen are consumed during a reaction. So 67.93 grams of O2. 1 mole O2 is 32 grams. And I have negative 198.2 kilojoules in this reaction, and it requires 1 mole of O2 for that. So 67.93 divided by 32 times negative 198.2, and that gives me negative 421 kilojoules. Moles, grams. Okay, awesome. Whew, that was fun. All right, so those are the things that I wanted to remind you of from the last lecture. Now, hopefully there are no questions about that, but if there are, call, email, drop by my WebEx, office hours, anything. Let me know, and we can talk about it, most definitely. So questions, comments, problems? Okay, and I'm going to pause here. We'll get started on our topic in just a few minutes. See you soon.